Okay, now let's take a look at calculating one of the beams in our structure, the cantilever beam I mentioned. This is the formulas or the amount of formulas that we're going to be developing. And I'll show you what that specific condition is. I'll drag over the Revit screen here. And remember, we're looking at this, in this specific example, we're looking at all of the loads that are applied on one of these elements. Let me see if I can zoom in here. So you can see that this is a cantilevered element that is carrying the load of that area there. So I'm just showing it here because it's clear. But we have one beam in between here that has to carry that tributary load. And we diagram it down here by showing that element now. Now we're looking at it face on from this view. And this is it in its transverse view. Now we can see that it's 32 by 32 because of the grid spacing. And this is the element that we're going to be looking at. And in this case, I guess maybe it's interesting to know kind of the scale of things here. This is 2 foot 4 inches between the top of steel and the top of the column. So this section of structure that we're looking at is a maximum of 2 foot 4 inches deep, which is very sizable, obviously. So now let's go ahead and put this aside. Remember the 32 and a half feet or 32.5 feet. And we'll move this over. So in order to calculate that tributary load, we need to, that's a square unit, so it's 32.5 times 32.5. That gives us basically 1,000 square feet. And we need to then figure out of that 1,000 square feet how much load is on per square foot. So there are other references for that. I'm going to bring on one which is a link to SkySieve. It's a calculator for a bunch of loading conditions, but this is just a quick map to show you this idea of snow loads. So here's a snow load map. Chicago sits down here somewhere, in this area here. So it looks like there's probably 25 pounds per square foot of snow load that needs to be taken into the calculation to meet that standard. And right now we're not picking the standards. All we're doing is just trying to get some approximations here. So that was 25, and I'm going to add in, let's say, another 15 for the structural weight of everything else that's going on. So I'm going to bump it up to 40 pounds per square foot. Implied roof from snow and the structural load. And multiplying those two out, obviously we get 42,000 pounds. And when we move to these larger volumes and we're in the thousands of pounds, what we typically do is we start to talk in kips. So that's 1,000 pounds or 1,000 pounds of force. So this is now reduced down by 3 decimal or 3 digits because it's 1,000. And so now we have 43.3 kips as we refer to it. So we take that implied weight and we divide out the length of the span, 32.5. This will be clear when I show you the web structural calculator. And we come up with this value of 1.3 kips per foot. So let's now go out to, I'm going to escape out of this. And we'll go to a web structural calculator. So this is webstructural.com. And I think if you just go to it, it will, let me just leave it for a minute just to make sure you can get there. And I believe there is, you go to multi-span beam design. And now we have the start of our calculation. And you'll notice our setup here, we have 1.0 kips per foot. And we had worked out that we wanted 1.3 kips per foot. So we're going to have to enter that value in. So I'll do that right away. I'll put this as 1.3. And the beam, let me see if I can, I'll save that and we'll come back to it. The beam is 32.5 feet. So I'll put in that number. 32 feet 6 inches. And you'll notice that number changes. And now we have to look at what our condition here is. I'm going to just change one just to show you. So if I click on this, it'll turn to fixed. If I click on it again, it'll be free. And a warning comes up and it says the beam is not stable, add another support. And that might be a little bit misleading because we have a pin connection here. I mean, you might think you need to put something else to hold it, but you can actually change this by clicking on it to a fixed connection. Now we have a moment connection and we can calculate it. We have our load in, we have our support condition, and we have our correct length, and we have some starting selection of a beam, and we can calculate it, and you'll notice that it fails in shear, in bending, and moment. So it's a colossal failure at first go round. And what's very interesting to note is this idea of the deflection. Some initial values that have been established for criteria by the codes or by the design setup is L over 360, and we're at L over 10. So we're down 227 inches. So this is bending way down under the load. It's much too small of a member. But this is only 8 inches high. And remember, we had that 2 foot something in our structure. I can look back at that. I think we had 2'4", so we had up to 28 inches of depth. So let's just jump to something that's much more robust of an I-beam. So we'll go up to that. We'll go up to that thickness of, let's say, 27, and we'll look at one of the lighter ones to start with, and we'll go ahead and calculate that. Now that's the actual depth that we have allowed in the visuals of our component. And it's still failing. And I guess what's important to note here is that in bending stresses, it's not. In shear, it's doing fine. But it is still deflecting a lot. It's deflecting 3.5 inches. Now, we're going to do some evaluation of that. We can take it up until it no longer fails. But we could also decide this L over 360 is too high a criteria for a maximum snow load condition. But that'll be up to really the discussions with the engineer. So you can see quickly how we can get this idea of, let's go ahead and we'll bump this up in weight and see if we can get closer to performance in this. And remember, we added a lot of steel and we're still added a lot of weight now. We've gone up to 194. These are really robust sections. I obviously don't want to, we're still not meeting the goal, but we're very close here. But this is a beam that is 235 pounds per foot. And what else is weighing into this, pun intended, is that it's also taking into the weight of the structure in that calculation. So every foot we're adding 235 pounds. So we've got a lot of dead load in this element. So really, this is a fine level of calculation, and how I would like to see this kind of presented would be to, if you're using Chrome, you could bop this down just a little bit so you get the whole thing on the screen, at least this whole here, and then just do a snippet of it, and then submit that to the blog to show that you've gone through and used this tool. And that would complete the structural component of the calculation. Now, if you're interested in not doing exactly what I have laid out, remember there is, you could look at trying to calculate the size of a column by using the charts that I had suggested in our lead into this. I'm trying to find you could go to these tables and just take the basic load that we've calculated that's already indicated on the drawing. So I can go back and show you that. Let me just grab this and move it over. And if we were to look here, we know that there's this column load here, and we know how it's expressed out over that. So you could just take this dimension, square it, figure out that same weight, and then find a column that can support that and make a suggestion for what you would choose. And then just do a screenshot of that from the booklet as you look for that. And you also know the length of it, and you know its end conditions, what its K value is. So all of that would be appearing in that chart. So that's an alternative piece of calculation for you to do for this project. So I'm not requiring you to do, if we go back to this overall assignment. I'm not going to require you to do these manual calculations and create spreadsheets. To preserve time and because of the general lack of interest that you guys had with doing structural calculations. But once again, the big takeaway is your ability to start to conceive about these loads, how they're played out. This idea of, for me, very critical, this idea of how a structural component appears in an assembly. This is a visual, like this can be 2 feet deep and still have a small appearance in a very tall building like this. So you know how much depth you can put in to create structure before it starts to look obtrusive or unattractive as far as the visuals go. So that would conclude the project.